So we are going to redefine stuff that you did in grade 10. You remember equations of a line, y equals mx plus b? Of course you do. So m was your slope and b was your y-intercept, and that made an equation of a line. And you could write this in many different forms. Now we're going to do the same thing, but use vectors. So we're going to think about our equation of our line, and we're going to redefine it for vectors. And what's going to be really nice is our equation of line y equals mx plus b, that only worked in 2 dimensions. But now we'll be able to define lines in 3 dimensions as well. So how does the idea work? So here I've got a line. It's going through the point A, it's going through the point R, and it's going through the point C. And somewhere you have an origin. So this could be in 2 dimensions or in 3 dimensions. And the way that we define an equation of a line with vectors is we say, take any point on the line. It doesn't matter where. So in this case, let's think about point A. That is the point on that line. And this vector, this green line, is going in the direction of A to C. Since C is another point on the line, does it make sense that A to C is the direction that the vector is going in? And depending on how far you go in that direction, right? If I make, here, maybe I can, perfect. Whoa, wait for it. There we go. I'm going to just take, if I make the length of this vector long enough, I could go all the way to C. If I make the length of this vector shorter, I could end at point R. If I multiplied it by a negative and switched its direction, I could go anywhere in this direction. So the way an equation of a line works, like when you had y equals mx plus b, you could plug in any value of x and find out what the corresponding value of y would be, and that would be a point on that line. The same thing happens here. We say we can plug in any value whatsoever that changes the length of this red vector. And if I change that length of that red vector, I'm going to hit every single point along the way. So what does that exactly look like when we're talking about vectors? Because here we have 3 position vectors. Position vector A, position vector C, and position vector R is any point on that line. So if I wanted to say find this point, I would have a position vector that would be for that point. And what your vector equation of a line does is it finds all of those position vectors. So we say R is any position vector which ends on that line. So there is our R. You take any point that is on your line to begin with, and it doesn't matter which one, which is a nice thing about a vector equation of a line. Unlike y equals mx plus b, where b is a specific point, a vector of equation lines says take any point on that line. So if we chose vector A, that's right here, any point on your line. C minus A is your direction. Does that make sense that if I wanted to say this direction from A to C, I'd have to go minus A plus C to get there? And that'll be my direction vector. So C minus A, we'll call this a direction vector because it's telling us which way that we're going. And then we put a scalar in front right here at t to say how long do you want to go in that direction. And if t is negative, it means turn around and go backwards in that direction. And if you have all the different values of t, you will get every single position vector along that line. So when t is 1, you end perfectly at C. When t is 2, you would go double. If t was 1/2, you'd end there. If t was 2/3, you'd end at that point. And by putting in all those values of t and plotting all those position vectors as you went along, you would make that line. And so we have a new way of writing an equation of a line using vectors. And the idea is, in order to, if I wanted to get to some point on this line from my origin, I first need to get to a point on that line. And then if I wanted to get to this point, I just have to go in the direction a certain distance. So once you're on the line and know the direction that line is going, you can get to any point by just going in that direction a certain distance. And this works for 2 dimensions or 3 dimensions. So we rewrite this with A, any vector on our line, B, that's your direction vector that you're going, and then that finds any point or any vector that would be on that line. So now we take this equation and we break it down. We can look at 2 dimensions or 3 dimensions, but if we think of R as being a point and A as being a point or a position vector and B as being a position vector, then looking at this equation and just looking at the x coordinates, we can say that x, highlighted here, the x coordinate is going to be this plus this times this, and your y coordinate is going to be this plus this times this. And these are called our parametric equations. So by breaking down the components, we get the parametric form of our equation. And from this parametric form, if you rearrange the parametric form to get t by itself, and then said, well, if t is equal to this and t is equal to this, then I can make these 2 parts here equal to each other. And that's called the Cartesian form. Because in the Cartesian form, you're taking out that t, and this is how you would rearrange something to get back to y equals mx plus b. So we're going to see how we can play around with starting with a vector and going back to y equals mx plus b and seeing what that looks like. So we want to find a vector equation of a line. What you need to find a vector equation of a line is 2 things. You need one point on that line, or one vector that's on that line, and you need the direction vector. Well, this question tells us already that one point on the line is 2, 5. And since it's parallel to 3 minus 4, this would be our equation of our line. So let's think back to grade 10. If you had this point on your line, and if it was parallel to 3I minus 4j, what does that mean? It's parallel to that vector. What would the slope of our line be? Close. Negative 4 over 3. Right? It'd have a negative slope. The rise is going down 4, 3 to the right, negative 4 over 3. How would you figure out this form of the equation using your grade 10 math? What would you do? Put your point in there. So we could put in 5 for y, 2 for x, and negative 4/3 for our slope. If we put all of the things that we know into that equation, we could rearrange this equation You would get 5 equals negative 8/3 plus b. Add the 8/3 to the other side, and you get 23 over 3 equals b. So there's our equation of our line in y equals mx plus b form. How many of you would have used the point slope way of finding this equation? Do you remember that? That's where you start with this equation where you plug in your slope and plug in your point. So our point was 2, 5, and then you would have to multiply this out, rearrange things, and you will get the same thing as your equation of your line y equals mx plus b. Now, how does that relate it to this? Well, first of all, I want you to notice that there's no not nice fractions in this. You're just dealing with nice numbers, something that is nice about a vector equation of a line. Your parametric forms, if we just look at the x-coordinate, it would be 2 plus 3t and your y-coordinates would be 5 minus 4t. Those would be your parametric forms of your equation. Your Cartesian form is once you have your parametric forms, can you see that if you solved for t in the first one, you would get x minus 2 divided by 3? Am I doing too many steps at once there, or is that okay? So I'm just taking my equation, my first equation here, x equals, I would minus 2 and divide by 3 to get t by itself. And if I did the same thing with our second equation, you would minus 5 and divide by negative 4. That's our Cartesian form. The Cartesian form is supposedly the same as y equals mx plus b. Well, let's check to see if it is. In order to check to see if it is, I would have to get y by itself. If I multiply both sides by 3 and both sides by negative 4, negative 4x plus 8 is equal to 3y minus 15. I want to get y by itself, so negative 4x plus 23 is equal to 3y. Divide by 3, and sure enough, we get the same equation. For vectors, the black stuff, that's review of before. For vectors, what we're going to mainly deal with is we're mainly going to deal with our equation of a line in vector form and our parametric form. The Cartesian form is just a way for us to transfer back to what our equations were from before. So here's one for you to try. So first of all, perpendicular. 3ij, oh, did I make a mistake here? Well, this is this, but if we need it perpendicular to this, it should be a flip here, right? And it doesn't matter where you put the negative, so that will change my Cartesian form as well here. There we go. So you get 2 minus t and 5 plus 3t, which will change these as well. Wow, beautiful. Cartesian form will be negative x plus 2 equal to y minus 5 divided by 3. So if we think back to grade 10 and how are all the different ways that you found equations of lines, sometimes you were given 2 points, sometimes you were given a point and a slope. The key thing is when you were trying to find y equals mx plus b, you always needed a point and the slope. The same thing is true for a vector equation of line. You always need a point and you need the direction vector. So the direction vector is sort of acting the same way as the slope. So here we're given 2 points that it passes through. So we definitely have the 1 point, but we have to figure out our direction vector. And if you're wanting to find your direction vector, well, that's going to be from A to B. How do you find out A to B? Well, you'd have to go negative A plus B. And again, if you're having trouble seeing that, draw out your picture. Draw A, draw B, somewhere put your origin. You would have to go negative A to get there, and a positive B to get from A to B. So our direction vector is going to be 4, 4. So when we're writing our vector equation of our line, we take any point, and it wouldn't matter if you chose A or B here, both would be right, plus a scalar times by our direction vector. And for a direction vector, it's not wrong to put 4, 4 here. It's not wrong to put 1, 1. Can you see that those are the same? This 4, 4 technically means your slope is 4 over 4. And if you had that as a slope, you might write that just as 1, because it could reduce to 1 over 1. So we can write it as 4 over 4. You could write it as 1 over 1. Those would all be equivalent things for the same equation. Now that we have this, if we're using this one, our parametric equations, well, our x-coordinate is going to be 1 plus 4t. Our y-coordinate is 4 plus 4t. And our Cartesian forms, x minus 1 over 4 and y minus 4 over 4. In 3 dimensions, the ideas stay the same. We just add another coordinate. So we still need to have a point on our line, and we still need to have our direction vector. So in 3 dimensions, if I want to find my direction vector from P to Q, well, that would be minus P plus Q. One, negative 5, negative 7 would be my direction vector. So I could take either of those points and now we have a way of describing something in 3 dimensionals for a line. Whereas before we've never really invented something like that from the past. Oh, didn't work. I just want to copy that equation. Copy. Oh, yeah. that's not what I wanted. Okay. There it is. Beautiful. There we go. So there's our equation from before. And the question is, does our point, or does this point lie on that line? If that point is on that line, then there must exist a value for t so that you can start at 1, 5, 3 and move in the direction of 1, -5, -7, either positive or negative, and end up at -1, 3, 5. The way that we show this is we say, well, my three parametric equations are this. I've got 1 plus t. My y-coordinate would be 5 minus 5t. And my z-coordinate would be 3 minus 7t. And if the point -1, 3, 5 was on that line, then what would, if -1 equals 1 plus t, that implies that t has to equal -2, right? If my x-coordinate needs to be -1, that only happens when t is equal to -2. And if t has to be -2 for the x-coordinate, we're going to check, does that happen with my y-coordinate? If my y-coordinate has to be 3, and 3 is equal to 5 minus 5t, is t still -2 in this case? And if we solve here, we get something different. We get t is 2/5. At this point, we already know that that point isn't on the line. In order for it to be on the line, t would have to equal the same thing so that you could travel in that direction a certain amount of time and get to that point. We don't even have to do the third one at this point. We can already say no. It's not on the line. So let's try another point. Is this point going to be on the line? So again, I'm going to steal my parametric equations from before. There are my parametric equations from before. So if my x-coordinate's 3, that would imply that t should be 2. If my y-coordinate is -5, that would imply that t is 2. And if my z-coordinate is 5, this would imply that t is -2/7. Oh, so close, right? Everything in your education from grade 1 to grade 12 told you the teacher would show you an example that worked after an example that didn't work. I'm sorry to disappoint. So again, we have to say no, it is not on the line. True or false? Your gut was like, this one's going to be on the line. Yes? All right. Just messing with you one more time. So all three of them have to equal the same thing in order for that point to be on the line. And this one was so close. What point should I have picked for this? If t was 2, I should have picked -11. You see, if I plug in 2 right here, then the z-coordinate should be -11 in order for that point to be on the line. And then when you show that all three of them work for t is 2, then you could say, yes, that point is on the line. This question just messes a little bit around with the form of the equation. If we wanted to rewrite this in the vector equation in this form, can you see that 3, 5 is a point on that line? And if I took out the t, my direction vector would be 2, negative 5. And then we bring back some old ideas. Do you remember what the unit vector was? A unit vector in the same direction as this line. First of all, what is the direction of this line? Two and negative 5. So the direction was the 2 and the negative 5. How do we make a unit vector in that same direction as that vector? What's that? 1 unit in that direction. How do you get it to be 1 unit in that direction? Or maybe it is already. Is that one 1 unit long? How long is this one? If we figure out how long this one is, 2 squared plus negative 5 squared, we find out that this one has a length of root 29. So our unit vector, we'd have to divide by that root 29. And now that would be, or that vector would have a length of 1. So to find our unit vector, we find the length of our vector and then divide by that. Find the Cartesian form of our vector. Well, to find our Cartesian form, we first find our parametric forms. Our x coordinate is equal to 3 plus 2t. Our y coordinate was 5 minus 5t. So our Cartesian form, solving for t in the first one, we'd subtract 3 on both sides and then divide by 2. Solving for t in our second equation, subtract 5 on both sides and divide by negative 5. So the first thing that we deal with in our vector equation of line is getting an understanding of, we just need a point and a direction that our vector goes in. Now that we have that idea, we can solve things that we solved in the past, like if you have 2 lines and they intersect, one of the things that you wanted to find out was where those lines intersected. How does that work when you have a vector equation of a line? So here we have 2 lines, L and M, and they're going to intersect. To find the position vector of their common point, we're going to look at their parametric equations. So on our L equation, our x coordinates, can you see that they're going to be 5 minus 4s. Our y coordinates are going to be 3 plus s, and our z coordinates are going to be 2s. And this is our line L. I'll switch colors here and think about our line M. On our line M, our x coordinates are negative 3 minus 4t. Our y coordinates are 7 minus t, and our z coordinates are just 6. From here, you need to take this information and figure out what s and t are, because if they intersect, the x coordinates need to be the same. So if our x coordinates need to be the same, I would get this equation. 5 minus 4s is equal to negative 3 minus 4t. And if I just had that equation, there's no way I could solve that because I have one equation with two variables. But I also know that my y coordinates have to be the same. So 3 plus s equals 7 minus t. And now I have a second equation with two variables that I don't know. And that might remind you of solving systems of equations where if you have two equations with two variables, you can solve that using substitution, elimination, or matrices. At this point, though, if you go right into that, that's fine. But I would say it's not bad to look at all of your equations, because if we had looked at our third equation, we can solve something right away. Because if our z coordinates also have to be the same, that means that 2s has to equal 6. So I could set up a system of equations and solve for s and t using the first three, but a little bit of common sense would say, I think I know what s is. S has to be 3. And once you have s is equal to 3, now you could plug it in either into equation 1 or into equation 2. Equation 2 looks like it has less math to do. So if I plug in 3 for s into equation 2, I get t has to equal 1. And once I know that s is 3 or t is 1, I can use either of my equations to figure out what x, y, and z are. If I was using my blue equations here, and I plug in 3 for s, can you see that I would get 5 minus 12, negative 7. 3 plus 3, 6. 2 times 3, 6. Had I used my green equation, then I would have to use t is equal to 1. If I plug in 1, I'm going to get negative 7, 6, and 6. And this is what should happen. You should get the same one on either one, because you want to find the point that they have in common. So we found the point that they have in common, and now we can also find the angle between those two lines. So remember from our dot product that the angle between two lines is the dot product of those two vectors divided by the length of those two vectors. Now the thing we have to consider is we have vector equations of lines here. We've got our blue line L, so I'll draw that here just so we can imagine it. In 3 dimensions, this is our blue line L. We had our green line M in 3 dimensions here. There is some point P where they intersected, which we figured out already was negative 7, 6, 6. And we want to find what is the angle between these two lines. In order to do that from the equation, the key thing is you must use the direction vectors because it's the direction of L and the direction of M, when they're put together, that's going to help you find the angle between them. So now we need to go back and think, well, what are my direction vectors for L, and what and m. So if I look here, can you see that your direction vector for L was -4, 1, 2? And your direction vector for m, if we go back here, is -4, -1, and 0. So we take our two direction vectors of our two lines, we can find the dot product of them, so 16 plus 1 plus 0. The length of our blue vector would be 16 plus 1 plus 4, square root of 21. The length of our green direction vector is square root of 17. And so we have that cos of theta is equal to 17 over root 21 times root 17. So to figure out our angle, go to our calculator. Cos inverse of 17 over root 21 times root 17 and in degrees we'd get 25.9 degrees. It wouldn't matter if you solved this one in radians or in degrees. Yes? Did I make a mistake? It's -1 and I wrote 1? Oh, it is -1 and I wrote 1. You're right. So then this would be -1, which makes this a 15. Retype this into our calculator. 37.5 degrees. Thank you. That -1 wouldn't change the length because we're squaring things. All right, so we have some practice questions. I'll give that out to you.